Okay, so let me welcome everyone to our weekly prac seminar of mathematical physics. And our today's speaker is going to be P.Batakidis, who is a researcher from the Aristotle University of Thessaloniki. And he's going to tell us about differential operators on Courant algebroids and Dorfman connections and the Atiyah class. So you are welcome to start.
Okay, thank you very much for coming to the talk. Thank you for the invitation to speak in the seminar. So as you see from the title, it basically has three parts. The first part will be to discuss a little bit what a definition of differential operators on Courant algebroid is, and for this we'll be generalizing a construction of Reuterberg, and then the second part has to do with Dorfman connections. I'll tell you what this is, and if we have time at the end, I'll talk a little bit about the Atiyah class. So that's the outline, basically, of the talk. First, we're going to talk about the Courant Dorfman algebra. I will not define it in the most abstract way. I will define it in the way that makes sense for Courant algebroids, because that's what I'm going to need in the talk. And you can think of it as an algebraic version of Courant algebroids if you don't like to do geometry. And then on this construction, we'll define a certain algebra of differential operators, which will generalize this Courant Dorfman algebra of the Courant algebra. So from the second bullet on, every Courant Dorfman algebra will be about a Courant algebra. Now, in the third bullet, let's say, we're going to define Dorfman connections of Courant algebroids, and there are a few features of these connections that are different. Most people use linear connections, study linear connections of Courant algebroids, and some things are straightforward when you do that. But we will discuss this at that point. The problem is always how to treat the curvature of a connection. Now, this might be premature in the talk, but you know that the curvature of a Courant algebroid is not a tensor. And imagine that if you start with a nonlinear connection, that's going to be even worse. So the idea is that you build. Sorry, is that a question or not? Okay, I thought there was a question. So the idea is that we build this algebra of differential operators so that all the calculus developed and induced by such nonlinear connections make sense. Like the curvature, theory derivatives of the curvature, they all live in the space of differential operators. And the last bullet will be about the motivation of what I discussed above, because when we started doing all these things, at first we wanted to define an Atiyah class for Manning pairs. A Manning pair is a pair of Courant algebroid and a Dirac structure. And I will start saying a few things about the Atiyah classes at that part of the talk, and then explain why it's hard to define it for Manning pairs. Although we know how to do that for many other cases, Manning pairs are completely different. Okay, so the motivation basically in the talk will come at the end, because it's in a way it's independent of what you will see in the first place. Okay, so I'm assuming that everyone, almost everyone, knows what a Courant algebra is. For what it takes, I mean, I have a definition here. It's just a vector bundle. You have two kinds of operation, non-linear, let's say, bilinear form, and this non-skew symmetric bracket. It satisfies these identities, and there is an extra map that comes along this DE. It satisfies this identity, and we will see a map like DE in a short while. But Okay, it's just a derivation. This DE, I'm thinking of it as a derivation on functions with values in some module of these functions. And we will construct another map like that in a while. So the problem with this structure is that although the right Leibniz identity works fine for this non-skew symmetric bracket, the left Leibniz identity is not as pretty. And this produces too many problems when you want to ask whether this can, I mean, higher construction on Courant algebroids can lead to tensors or not, and so on. So that's one of the problems that will be underlying everything I'm going to talk about next. So about Courant algebroids, the main things that I will have to recall is that due to Rothenberg, there is a correspondence between these kind of structures, and you can think of them as a graded symbolic structure, a graded symbolic manifold, and this graded symbolic structure is encoded in this function that we usually denote as theta. It's commuting with itself with the induced Poisson bracket, and then you want to better understand what the algebra of functions on this graded symbolic manifold is. And the idea to do that is to start thinking more abstractly, more algebraically. And Rothenberg's idea basically was to construct an object for Courant algebroids like Lee-Reinhardt algebras for Lie algebroids. Like a Lie-Reinhardt algebra is something completely algebraic, but every Lie algebroid corresponds to a Lie-Reinhardt algebra. And that was missing. The algebraic object was missing at that time, the one corresponding to Courant algebroids, and that's exactly what the Courant algebra is. You can think of it as an analog of what a Lie-Reinhardt algebra is for a Lie algebroid. You can think of it as an analog for Courant algebra. So as I said, I will not define the most abstract way what a Courant Dorfman algebra is. In the next slide, I will just say the basic ingredients. These are on the left with the blue colors, and on the right with the red color, it's what you can think of a Courant algebra to be only for Courant algebras. Like if you've seen the definition of Lie-Reinhardt algebra, you immediately think of a Lie algebra. Okay, it's obvious, and more or less the same thing happens here. So on the left, in general, for what you need to define a Courant Dorfman algebra is a commutative algebra. In our module, I have a metric, secondary algebra, a derivation of the algebra with values in that module and a Dorfman bracket on it, right? And all these structures have to satisfy conditions that we more or less saw before in the definition of a Courant algebra. Now, if you take the Courant Dorfman algebra precisely of a Courant algebra, that's very specific. It's not very specific, but it's obvious how to think of these objects on the left, right? The commutative algebra would just be the algebra of functions on the manifold. The module E will be sections of your bundle. You have the non-degenerate symmetric bilinear form. This map, this derivation DE that we saw in the definition, and the skew-symmetric, non-skew-symmetric bracket in the definition of a Courant algebra. So from now on, a Courant Dorfman algebra for us will be what you see on the right. Okay, it will be a Courant Dorfman algebra built from everything you have already from the definition of a Courant algebra, and it will satisfy the same conditions that you expect. Okay, but to understand this algebra, I have to be a little bit more precise about what the elements are of this algebra, what is the product. It actually has more structure. There is a differential on it. So I'll take the next few slides to explain a little bit what all these things are. So let's first talk about the elements, right? What are the elements in this algebra? So this CP is an index we will see what the role of this is. So elements in this thing are just finite sequences of omega i's. Okay, so you have an omega, this is an element in CP, and it's composed of, you see all these guys here, and every omega k is a map like that. Now, here, what we have to remember, at least in the future, is that these omega k's take two kinds of variables. There are the variables from sections of your Courant algebroid, okay, that carry powers of this module. And then it also takes symmetric powers of one forms. So there are two kinds of variables for omega k. But omega k, whatever the variables you give it to, takes values in the smooth functions of the method. Okay. Now, if you want such an omega to be in CP, cannot these omega k's cannot just be anything. And that's the exercise of conditions. There are these three conditions they need to satisfy. The first one is that each omega k, this finite sequence, has to be a symmetric k derivation of these forms on, let's say, the second kind of variables. And then there are two identities that we have to read now in a certain way, and I'll tell you how. First one says how you can fix two neighboring entries from your two neighboring sections of your Courant algebra. So as you feed it to make it, take EI and EI plus 1. Because we are order this 0. And there's a term coming out in the second variables, that's the derivative, say, of this function. Yeah, it's a bit technical. What we have to remember, at least as an idea, is the second this omega kids. The formula is not that important. What is important is to see here that these omega k's are in fact first order differential operators for the sections of the Courant output. Most usually, when you want to define what your first order operator is, feed the function to some slot, like EI, where EI is, and then you take the difference of whatever this is linear, then you call this omega k first order differential operator. So the third one, but what it means for me is omega k is the first order differential operator on the entries from. And the formula to still do exactly what kind of sort of differential operator is. It tells you the symbol of this operator. So the definition of Roy is that the Courant Dorfman algebra of the Courant algebroid is a collection of all these finite sequences for writing P, given that the terms in the finite sequence satisfy these three conditions. Okay. Now, in this slide, we see what the elements are. So Courant algebra, but we haven't said anything before. Okay, so just take a few instances to what the product looks like. Again, it's not important for
Panagiotis, people have some kind of problem with sound. So, do you have a good internet connection? Could you like try to switch from Wi-Fi to a cable or something like that?
Yeah, I can move. Just give me 1 second to try to move.
Because we have, we can see the presentation all right, but we have trouble hearing you, your sound. Okay. It's like really poor quality.
Yeah, I'll move for 2 seconds. Give me.
Mm-hmm.
in about 30 seconds.
Okay.
Okay, thank you. Can you hear me better now?
Yes, it's very good actually. So
Okay, thanks.
I hope everyone can.
Is there some part you'd like me to repeat? Maybe?
So maybe during the talk, if someone has some unclarities, feel free to ask.
Okay.
And just
Okay,
continue.
okay.
Yes. Thank
Okay.
you.
So, okay, so I was saying that we saw a little bit what the elements of this algebra have to look like. What does the product of this algebra looks like? If you take an element in this CP and you take an element in this C cube, the product of them will be again a finite sequence with the right length. And each one of these terms now, from omega times eta naught up until the last one, is defined by some kind of shuffle slash convolution product that you see here. Okay, so I'm just writing down the formula just to see it. It's not, I will not do any calculations with it in the talk, but it's not that strange. Okay, that's my only point. And all this algebra now, there is also a differential that takes some omega, a finite sequence like that, and it's of degree 1. It gives you another finite sequence, and it is defined. If you look a little bit what the formula looks like, you will see that you need all these structures from your Courant algebra. Remember, we're talking about the Courant Dorfman algebra of a Courant algebra, not any Dorfman algebra. So besides this differential, there's also constructions. Remember again that you have two types of variables for these sequences, variables from the Courant algebroid, sections of the Courant algebroid, and one forms. So there are two ways you can construct an omega like that, and they become, both of these constructions, they become graded endomorphisms of this Courant Dorfman algebra, and eventually all these three operators together, the two constructions and the derivative, and there is also a Lie derivative you can define, they make up for a Cartan calculus that you can perform in this Courant Dorfman algebra. Okay, so more or less that's what it is, and I'll move now to the differential operators of on C, let's say, on this Courant Dorfman algebra. Now, the model space will be this Gothic D, and P will be the same index as before. I will use it in the same way. More or less tells you what the length of a finite sequence of an element in this space is. Again, these terms in this finite sequence look like the maps you had before. There are two kinds of variables they can take in, either sections from your Courant algebroid or one forms. The difference than before is that now they're not, you can take them to be higher order differential operators. So in a fancy way, that's what I'm writing here. And this is what tells you what these lower indices tell you. Okay, they tell you the order up to which you can derive sections of E and one forms here. So basically, it's one of these omega k. If it is on this space with lower index m and m minus 1, it has to be a differential operator of order m on these variables, and a little bit different differential operator on order m up to order m in the first p minus 2k minus 1 arguments, and order m minus 1 in the last argument of this part of omega. And this is like, it's clear what the generalization than before is, because for Reutenberg, for just a Courant Dorfman algebra, you had m equals 1 over here. If I take m equals 1 over here, I get the Courant Dorfman algebra back. Okay. Again, I'm just allowing higher order derivations of these objects. So the definition we have for this algebra of operators is, again, that the collection of all these spaces for every p and every order of differentiation you want makes up an algebra, and that's what we call differential operators of the Courant-Dorfman algebra. Okay. So I'm following the same line as I was doing before. I first discussed the elements of this new thing. And this is because this is the basic difference there before, because you can extend the product, you can extend the differential and the constructions that you had before in a more or less natural way. You can extend them from the Courant-Dorfman algebra to D, to the differential operators, and then this D becomes a graded algebra, and with the extended differential, it becomes a cochain complex. So there is a cohomology attached to it, right? This is what we call the complex of differential operators, and the cohomology of differential operators, and so on and so on. Okay. Now the reason to do all that will appear after we say a few things about Dorfman connections. So I cannot define Dorfman connections right away because you need more structure to define it. It's not only about a Courant algebroid. You need a second a companion bundle with it, and that's what we call the pre-dual of E. So the pre-dual of E is it's another bundle. E, you start with a Courant algebroid. Okay, that's what the first bullet says. And B, we take it to be a smooth vector bundle of constant rank. And there is a pairing between these two, but not necessarily non-degenerate. Okay, actually, it's trivial. I mean, it's a trivial case if it is non-degenerate, so you take it to be possibly degenerate. And there is a map in the definition of a pre-dual vector bundle, this DB, which works a little bit like DE, the map you had in the definition of a Courant algebra. It's a derivation of these algebra functions. It takes values in sections of B, and it satisfies this identity. Okay, but remember, it's not non-degenerate. So all this put together is what the definition of a pre-dual of C is. Okay, and if you think, well, it's not actually that trivial to see. It takes a proof for it, but actually DB is not something. It's basically built on just a de Rham differential of forms. Like, it's actually, you can prove that it's a composition like that for some alpha vector bundle map from T star M to B. Okay, but it is true that DB looks like that. So if you want to forget it and just think of it as this composition over here, that's okay. Now, the Dorfman connection is something that you can define for a Courant algebroid and a pre-dual vector bundle. And that's the definition. Um, we were not the first to define Dorfman connections. Madeleine Zotz was the first one to do it for dual algebroids. But the difference, there is a small difference in what we had to do is that we took the condition for DB actually to be a derivation is something we added for other things to make sense. So it's not entirely the same in the sense that our definitions of pre-dual bundles are not entirely the same. But if you just isolate the, our our definition of a Dorfman algebra, a Dorfman connection, I'm sorry, you will see the same thing. So what is a Dorfman connection? A neat Dorfman connection on this B, E has to be a Courant algebroid, B a pre-dual of E, and then you have this nabla, which, as you see here in the three conditions that I'm asking from it, is not linear. Okay, the second condition is the usual one for connections, but it's not linear on the first entry. And you know exactly how it's not linear. This terms here tells you the symbol. Again, if you think of this guy as a first order differential operator, okay, if it's not linear, it's first order, and this is the symbol. And the third condition is some you can think of it as some stability condition that it stabilizes the image of DB in a sense. You can think of it like that. But it's also necessary actually. Okay, it's not. It has a purpose for being there. Okay, so from this slide we can just keep and remember that we're now talking about nonlinear connections of Courant algebroids. You could take B to be the Courant algebroid itself. In that case, you will have this double angle bracket to be just the bracket in the bilinear form in the definition of Courant algebra, but this is very restrictive. I mean, it's more or less trivial. In general, be something else. Okay, usually we'll take it in examples. We take it to be some quotient of E or some direct sum of E with something else, and so on. So, actually, the first proposition that I want to mention is that it's not at all trivial to show that actually the set of Dorfman connections is not empty. Okay. Eventually, you have to build some nonlinear PDEs and make sure that they do have solutions. That's the whole point. But that's our first result. And then you can also show that this set is in a affine space, and we also have a model vector space for this affine space. I just didn't write it over here because I don't need it for what I'm going to do next. Now, the two easiest examples of a Dorfman connection is one that you can construct from just a classical linear connection on TM. If you take the standard Courant algebroid here and just a linear connection on TM, you can build a Dorfman connection on E as an easy example with this formula over here. I mean, you can take all the properties that they're satisfied. But the next not so trivial but also very motivating example is what people call the Dorfman connection. And this is interesting because okay, I'll just talk about the example and then tell you why it's interesting. So a Manin pair, as we said, is a pair of a Courant algebroid E and a Dirac structure. This is what I'm denoting as L over here. And the both Dorfman connection is a connection from L on the quotient defined like that. So you taking the connection on the quotient by taking the quotient of the bracket of L with E. Now, the idea for this connection basically came from the case of Lie algebroids. if you had a Lie pair, and I mean that if here you had just a Lie algebroid, let's call it again E for simplicity, and L was some Lie subalgebroid of phi, then this connection would be linear. Okay, with the same definition. Here you would have the Lie algebroid bracket, but the same connection would be linear, and a part of the curvature of this connection actually is what people call the Atiyah cocycle of this pair of Lie algebroid. So this is a little bit the way we're gonna introduce ourselves to the last part of the talk, where we have to deal with Atiyah classes. Okay. All right. So okay, let me change this slide. So you have defined what a Dorfman connection is. Then you ask yourself, what about the curvature? Is it making sense? What kind of identities are true? And the truth is that there is a derivative that you can define, taking multiples. It satisfies the same Leibniz identity as you would expect. See, here I'm taking a product of omega with B. B, it's a section of my pre-dual vector bundle. And so here's the interesting thing, that if you simply define, you take the curvature of this Dorfman connection to be just the square of this derivative, it's pretty much sure that you expect not to get some tensor, right? Because this was not going to happen anyway for linear Courant algebraic connections. But here on top of that, your connection is not linear, so it's going to be messed up even worse. But the interesting thing is that if you take the square of this Dorfman connection, the space you arriving in is actually one of these spaces that we have constructed before. So the notation here is that you have a space of differential operators on your Courant algebroid. The detailed definition that I showed you before was about differential operators taking values in the space of, in the algebra of functions on the manifold. The only difference here is that I'm taking values in sections of B. Okay? Everything else is pretty much the same. But the point is that the same way you have entries of this object, when I feed it a section of B, uh, the properties they have, it's exactly the same that I had before for my differential operators. I mean, they are of a precise order in every entry. And these two identities is something that you can prove actually, and look like the ordinary, let's say, Lie algebroid case, that if you contract this object here, say I'm feeding it a section of B, so now I live in this space. If I contract with two sections of my Courant algebroid, then this is what you get. Okay. And also you can contract with some function or equivalently an exact form. This is what you will get. And there are other papers in the area where people basically didn't know what to do with terms like that, because the moment you start computing and trying to understand what the higher powers of this exterior derivative are, uh, these terms, they produce actually terms that you don't know how to fit in, to group together. Right? So what we decided to do, it's basically, even though we had a nonlinear connection, we decided that we are not going to try to correct anything, like either with some basic curvature or some Galtgary type of definition for the curvature. We're not going to try to correct anything. We'll just see any term that comes up. Okay, we'll just keep every term that comes up in the definition. We'll just try to make them make sense in some appropriate ambient space. Okay, and that's why we constructed this algebra of differential operators. Another way to look at these two equations in blue is that as an element in here, okay, in this space on the right, your curvature has to be described by some some finite sequence of maps, and these two maps are what we call R0 and R1. Okay, and yeah, in these two lines, I'm just rewriting the blue equations. And the interesting thing is that all your contractions, the ones that you see already here, both for E's and F's, the derivative that there is a differential that comes up in the space of endomorphisms of B and so on. You try to mimic all the ordinary differential geometry, and actually it's not so obvious, but it is true that you have a Bianchi identity, even for objects which are not tensors. They're pretty far away from being tensors. Okay. Okay. So, I think how much time do you think I have? About 5 minutes or 10 or 5?
I would say more like 15 minutes. Yes. So we have
15.
yes,
Okay, okay, that's very nice. I'll probably be maybe went a bit too fast. Okay, so okay, now let me start saying a short story about Atiyah classes. Okay, now an Atiyah class, before I go on to the slides, is something that comes from almost 60 years ago. It was defined by Atiyah himself, and it has seen, like, for 40 years, some until the late 90s, there was not much interest, not much progress about it. And then there were two papers from Konchevitz and Kapranov, and they showed some remarkable properties of this class related to complex manifolds, holomorphic connections, difflow isomorphism in representation theory. That's another talk, and I'm not interested in that now. But since the late 90s, people started working a lot with the Atiyah class in different contexts, and they were trying to generalize it to a little bit more general settings and so on. And at this point, the point we're at, the definition of the Atiyah class for differential graded geometry is more or less the most general object we have related to this. So I will go directly to that because I'm assuming most of the audience is acquainted with differential graded geometry. So let's see what this is. And you have to remember that even when you're not talking about differential graded geometry, like in classical settings of Lie algebroids together with Lie subalgebroids, the Atiyah class it's a cohomology class. We will see that in the theorem. And it's a cohomology class of a cocycle that represents a part of some curvature. It's a part of some curvature. Okay. So it will be the same thing here. Okay. So start with a DG vector bundle. We have like a graded vector bundle. I'm just probably you already know these things. I'm just reminding them. It's a graded vector bundle with a linear homological vector field. Okay, let's call this curl E. I hope there is no confusion with my notation before. And a DG Lie algebroid is just a Lie algebroid in this category. Okay, it's a Lie algebroid in the category of DG vector bundles. All right. So the theorem / definition of these people, Mehta, Stianon, and Shuv, back from 2015, is that when you have a DG algebroid and a DG vector bundle over some graded manifold, curly M, and a connection of this DG algebroid on E, in your vector bundle, then you take this map. Okay, take this map here. It's clearly defined, and you can prove the following things. And the way this theorem is stated is like let's say the universal way you can prove a theorem about something that you want to call the Atiyah class of something. Okay, and what are the parts of this theorem? First is that this map is a degree 1 section of this home space. Okay, from the product L with E with values in E. This space actually has a homological vector field on it. You can build it from a combination of the homological vector fields you have on L and E. And alpha nabla is actually a one cocycle for this homological vector field. So there is a class defined for this alpha, and you can show that this cohomology class is actually independent of the connection you chose. Okay? So these are the 3 bits, again, 3, let's say, characteristics that you want to show for every candidate, if you want to call it the Atiyah class or cocycle of some. Now, I'm gonna state a few results in the area, and hopefully you see in a couple of slides why it's hard to discuss the Atiyah class for many in Paris. Like in the setting that I was up until a while ago, Courant algebroids and Dirac structures, why is it so hard to define what the Atiyah class is? So the first theorem is by myself with Yannick Vogler from 2018. And we're just building DG Lie algebroid structures on tangent spaces of graded vector bundles. And a Lie pair that I'm assuming at the beginning of the statement is, again, just a Lie algebroid L with a Lie subalgebroid A. And we show that this direct sum is a DG manifold, and all these this inclusion and projection behave well as a DG manifold morphemes. And in fact, that's the most important thing, is that the inclusion, the injection, actually induces a quasi-isomorphism between the DG geometric Atiyah class that you saw in the previous slide and the ordinary Lie pair Atiyah class. Now, all these objects actually are not that old. Like even the ordinary, the Lie pair Atiyah class that I'm mentioning over there was only, I think, defined in a paper that was published in 2016, but it was already online, I think, from 2013. So we're talking about what happened only in the last decade. Now, the next result I want to mention is it's more recent. And again, as you see here, people are trying to understand the ordinary definitions and properties of Atiyah classes within the DG language, in the DG geometry world. Okay, that's a pull-apart construction that simplifies too many things that we had before. More or less, that's the whole point. And the last theorem in the slide is, I think Sylvain was giving a talk in the seminar about something else, maybe a few weeks ago. It's a result about generalization of the Atiyah class, not for just pairs of Lie algebroids with ordinary Lie algebroid representations, but for representations of Lie algebroids up to homotopy. So a Ruth here, what I call a Ruth here, is just a representation up to homotopy of a Lie algebroid. Okay, and the result is that you do have an Atiyah cocyclium theorem for this more general case that works the same way you would like, and of course it contains all the the ordinary representations that we knew from before. Okay, and I think I'm close to the end. Maybe I'll skip the first statement here. I just want to recall a statement by P.Batakidis and Jonke, also a very recent result, which explain actually also what the physical uh, uh, importance is about this Atiyah cocycle. This alpha nabla is exactly the same cocycle that I showed you two slides before. So the result is that if you have this manifold with this curly Q as a homological vector field and torsionless connection, then you can see these elements, the higher gauge theory and field strengths. The transformations basically are described. Okay, this map was known before, that it's described in this curly Q, but it's also inside. You can find this information inside this Atiyah cocycle. Okay, so I'm close to the end. Just want to discuss a little bit uh, why these things are interesting. Every connection we apart from Dorfman connections that I was discussing at the beginning, when you have to discuss Atiyah class, in every context we know so far, all the connections are linear. Okay, for Lie pairs, I mean Lie algebroids with Lie subalgebroids, complex manifolds. We know what the Atiyah class of a complex manifold and a holomorphic vector bundle, what it is. For L infinity algebras, we know that as well. Regular foliations, you can define it in too many settings. But every time the connection you're using and you're working with is linear. Now, there is a problem already that people are trying to correct and find meaningful definitions for the curvature of Courant algebroids. And this is already not an easy task if you think of linear connections of Courant algebroids. But why is it interesting to discuss? Why are we looking for the Atiyah class of man pairs? It's because we want to define it for generalized geometry. Okay, that's the whole point. For generalized complex geometry, you can model this with uh, a Courant algebroid and a Dirac structure. So if you can do that, it's a vast generalization of the setting that you had before. But the problem is that if you're talking about man in pairs, you're talking about things that are not in the same category. I mean, uh, they're not of the same nature. Okay, so you have a Courant algebroid and a Dirac structure. Well, a Dirac structure is a little bit simpler than a Courant algebroid. It's actually a Lie algebroid. Okay, so it's these two are not fitting well together, and what we are attempting to do is like somehow make them all live in more general spaces than you would like in order to have tensors and accept all the extra terms that you have in your formulas and calculations, as long as at the end you can prove a theorem of the Atiyah type that I showed you before. Okay, so this is how we started uh, taking Dorfman connections because we had the example of both Dorfman connection, and we were trying to have a theorem like that, but at some point we realized that the calculus we were using had to be established from scratch. Like it's completely different. You now have differential operators everywhere. So that's what I showed you in the first part, and this um, this Atiyah related work is still ongoing. I mean, it's not finished. And there's one more comment I'd like to do. The one of the problems might be that we don't have a graded picture of what you saw in the first part of the talk. Okay, we don't have a graded picture of what a Dorfman connection looks like. How do you describe it in a graded geometric way? You can define a Courant algebroid in a graded geometric way, but we don't know how to do that for the other components, like the pair of a Courant algebroid with a pre-dual vector bundle, what a Dorfman connection is. We don't know how to do that. If we knew how to, if anyone knew how to do that, then another strategy would be to try to define the Atiyah class of a Manning pair using this theorem over here. Okay, like in the DG world. But I think this is even more far than where we are in doing that. Okay, but that was just one last comment. So these are more or less the basic references I used in the talk. The first one is the original paper by Atiyah, where the class first appeared. Then the second paper is what I discussed, joint work with Fanny Petalidou. The third paper is where the Atiyah class of E pairs were first appeared. It's from 2016, but again, I think the first version in archive was from 2012. The first definition of Dorfman connection and for dual algebroids a bit different than what we're doing. First appeared in this paper by Madeleine Zotz. The paper from Gerald Waldman is another place where you could see where a Courant Dorfman algebra is not the same construction as Reudenberg. That's in the last reference here. It's not exactly the same construction, but in the smooth category, we know that they're equivalent. Okay, the Courant Dorfman algebra in both papers, it's equivalent where you are in a smooth category, and that's where we're working. So I think that's that's all I wanted to say. I hope I'm in time and not too fast. Thank you.
Yes, thank you for your talk. Now, if someone has any questions, now is the time. Yes.
So I have just a quick question. What is an algebraization of the notion of a pre-dual bundle in terms of Dorfman algebra?
I'm sorry, can you repeat that or come closer to the microphone because it was a bit blurry.
Yeah, just a moment. Okay, so I was wondering what is the algebraization of the notion of a pre-dual bundle in terms of the Courant Dorfman algebra? So it's a module subject to some conditions. So what those conditions are?
That's a good question. I don't think it has to be something. Well, it has to be something different because, in principle, it's not necessarily related to E at all. In most examples that we have in the paper, it's some quotient of E or some direct sum of E with something else. But in principle, it could be something completely irrelevant to your Courant algebra. But the Courant Dorfman algebra is defined and constructed only using the Courant algebra structure. You don't need something else. So I think what the idea of your question is to have another construction like Reudenberg's for B, for the PGO bundle, and this I haven't thought about it actually.
Yes, thank you.
Oh, that's
Okay. Any other questions? Just look into the chat. So I guess there are no more questions, so we can thank the speaker again.
Okay, thank you very much.
Okay. Yes, and thank you everyone for joining
Okay.
seminar, and we will see you the next week, I guess.
Okay. Have a nice afternoon.
Goodbye.
Bye-bye.
Bye, thank you.
Thank you.
Bye.
Bye-bye.